And it's very nice to come back. Okay, it's been 2.5 years. So I'm thinking about the Leeds all the time. Okay.
Ronnie, if you can say
Yeah.
so people can hear you and see you.
Yeah, and it's been a long 2.5 years. Okay. But I'm very glad, to come back and to see, right, the groups that are being expanded. And now we have the LEDTech, right? It's very new to me. And after, Sufi and Hannah's introduction, so I know the group is growing. Okay, that is very fantastic news, right? Is for the people to study the color science. Okay, so I'm a color scientist, but today, right, I'm going to talk about color and imaging science. That is Ronnier Luo's perspective. Okay, if you disagree, fine. Okay, right. But I'm going to be very much, right, focused on the spectral imaging. Right, next, please. So I'm going to talk about the, right, is the types of the color reproduction. So this is my mentor, right, Bob Hunt. Starting from the, right, is the, 61, and his first book on the color reproductions, okay? And then after 10 years, 70, that is the first time, right, is this, types of the reproduction being introduced. That is formed, right, is the basis about the color technology, right? So I'm going to talk about this, the types of the technology. And after that, right, I will talk about the research in my lab, but it's also the projection about the color science that should go, right? And finally, right, all this, right, is the color science is applied science. So our job, right, is to spin off, and we can produce the useful, valuable technology for industry, okay? So the technology I'm going to introduce, right, is lighting, vision, camera sensors, and the object. And each one, we provide a solution for that, okay? Next, please. So everybody see this, okay, Ronnier Luo is coming, okay? How do we see colors? We need 3 elements. We got the light source, we got an object, and then we got a human vision systems, okay? So this is, right, is the how CIE, the had I introduced, right, is the how, what is the fundamental of the CIE systems, okay? And, this is, XYZ, okay? So what is XYZ? The CIE defined each element in terms of spectral. So to define the light source, we have spectral power distribution, SPD. For the object, we have reflectance. For the human vision system, we have standard observers, okay? So all these are the mathematical functions. We multiply them wavelengths by wavelengths, and finally we sum up XYZ, okay? It's representing, right, any color or light, how much red, how much green, and how much blue in order to reproduce these colors, okay? So now, right, I forgot to mention, right, is the Suchen's here, okay? Suchen is representing textile industry, Martin Spencer, leading technologist, okay? And we work on this for many, many years, how we can get it right, how we can get the color reproduced. So what that means, right? CIE gives you a good solution. I have 2 objects, XYZ1, XYZ2. If they equal, what's that mean? They match. It's a successful color reproduction is being achieved, okay? The next, please. So then, I'm sorry, it's Ronnier Luo's map again, okay? So I believe, right, the most important color reproduction, the CIE publication, right, is the colorimetry, 4th edition, okay? So the white ones, right, so this is, right, is all being provided. How do you calculate the XYZ? So you need a spectral power distribution, you need a 2-degree, 10-degree observers, you need how do you measure the spectral, for an object, you got a CLAB, and finally, right, you got a CIED 2000. Suchen, you will disagree that you think the CMC is better. Okay, I will tell you the E2000 is a lot better. Okay, but that's different story, okay? But now, right, what the life goes on, we move into the color appearance period. Okay, appearance matching. You use the mobile phone, right? You use it in the morning, look at the images, and you look at the same images at night. They don't look the same, but they need to be the same. This is what we call the appearance match, okay? And then, right, to do the appearance, we also need the uniform color space. So Chem16 UCS is what we are doing, okay? So CIE is doing a lot of work in blue. That means, right, it's in the overall color industries, we still need the chromatic adaptation transform with proper D values. That means adapting in different conditions. The whiteness, vividness steps, okay? And the color contrast, HDR, and the WCG. The high dynamic range and the wide color gamma displays. So all this, right, because we have the product and there is the strong industrial demand and we need a new tool for that. So CLAB is not useful, right? So we need a color appearance model and also UCS, and we provide a solution for the overall industries, okay? So a lot of my work, right, is to do with mobile phone, okay? My good mobile phone is in different pocket, okay? This is the, very old mobile phone, okay? And here on your right, is saying color is not enough because, right, we need the total appearance. Total appearance include texture, gloss, and also translucencies, okay? So what we are doing now, right, is to go beyond the color, and then we are doing the total appearance of the product designs, okay? So you need to have the, how much gloss, how rough is texture, and also, right, how the light can go through. So the combination of all this, the information is final total appearance, okay? So this is the lab. All this, right, is the function we are doing, okay? And why we're doing this? Next, please. Wow, I take it out, okay. But anyway, we do a lot of this, right? It's very much focused on the mobile industries, okay? So it includes, right, how can we capture the images accurately? How can we reproduce the on-screen? And how we can make the images beautiful, okay? So, hey, sorry, can we go back again, okay?
You just did that automatically.
Yeah, so types of the color reproduction, right, 161, okay? So look at so nowadays, right, you are buying things, right, on mobile phone every day, everywhere, okay? So this is what happens, in Far East, okay? So everywhere we go, we have a mobile phone. We pay money, we select the goods, okay? Why we go to the, at the shop? Because we want to know what it feels, all this. And then we compare the price. And finally, right, we make the purchasing, okay? So it's sort of the, combinations, okay? But how can we, get the colors right, okay? 6 types of the color reproduction, okay? I go back to the original proposal, okay? It's now all being fulfilled, okay? Number 1 is a spectral. Every object, right, the fingerprint is the spectral. You must get the spectral right in order to get the, accurate color reproduction. But it's very expensive. It's the most expensive way to do the color reproduction. Colorimetric, we have relative and absolute, right? So you capture an image in such weather, outdoor images, very, very bright. However, your display is very limited the luminance range. So your only way to do it, right, you compress the whole images into the small screen. Okay? So this is what we call relative. The relative, right, is very much depending on the white point. Okay? So I look at this, the sky is very bright. I take that as the white. So I will know the XYZ value of the white. And then I compress that white into my displayed white. So everything, right, the images, right, is coming to place, okay? coming into place. Absolute. Now we got the better facilities. We got the high dynamic range displayed, very wide color gamut. Okay, we can achieve the 1,000 candela per square meter. That's very bright. Strictly, it's not as bright as what we see now. Outside, we're talking about 30,000 candela per square meters. Okay, but even that, right, is that we can produce the much better, quality images. Okay, right. So can we produce the very high dynamic range to mimic the outdoor situation? I think it's coming, but never be as bright as that. Now we have the laser display is coming. We have very much the bigger is wide range, okay, and very bright. We can go to the 5,000, 6,000, okay. Then the question is coming: do we really need that? Okay, so you look at the screen, we have very bright light shining to you. You don't feel comfort. How can we make all this together? Okay, and then it's appearance. Okay, so this is what we are very proud of, right? Color appearance model is being developed over the years and being widely used in the imaging industry. So how we apply this, right, in the mobile industry. So you capture images in the daytime, it's bright. But if you look at night, it's too bright. So we can reduce the brightness until they got in what we call the appearance match. Okay. So what do we do, right? We call JAB or LAB match. So what you captured in the daylight, very bright, and then you normalize, you got the LAB, and then at night you recompute the white points and bring everything down in order to have a very good appearance match. There are more, functions for that, but this is just an example I gave to you. So appearance match is important for color reproductions. Okay, right. And the top, the fourth, right, is what we call fidelity. So what does that mean? What you capture and what you displayed, they need to match. So it's a fidelity. You need to get the color right. But how about the users? Do they want accurate colors? No, they want the preferred colors. Okay, what is the preference of colors? I want my face to look beautiful, right? Okay, and I want, right, is the dull day to look like in the bright sunny days. Can we do it? Yes, we can. You need a preference models. We call the preferred color reproductions. And also, right, we have an atmosphere, okay? I don't like all this. I want this, the restaurant looks romantic. I want this, the dishes look delicious, okay? So this is what we call the atmosphere. You can find it in your mobile phone now. Atmosphere reproduction is there. You can create your own, feelings, okay? So all these are different types of the color reproduction. But today I will be very focused on the first one, spectral, okay? Every object, when you produce this, there is only one fingerprint. That is your spectral reflectance. Yeah. So if I can capture the image, I can get your face and all your reflectance coming out, right? And I can reproduce your face accurately in all conditions. Why is that? Because this is what we call metameric, okay? And metameric, opposite of that is the metameric, non-metameric match, okay? That is what we want. We want to take pictures of the Van Gogh's paintings and reproduce it in all different light sources. They look exactly the same or very close to the original. How can we achieve that? Spectral reproductions, okay? Everybody knows that, right? So we spin off the different technology, right? So, and our goal is to personalize the mobile phone, okay? Mobile phone is your friend. Its goal with you forever. It represents you. How it displays, you like it. Everybody's the display is different. It's depending on your gender, it's depending on your age, it's depending on your preference of colors, okay? So this is right, is how do we achieve that? The first one, the camera, okay? So we have the camera there, okay, camera, okay? So camera just like the, human beings. It got, we got the color matching functions, X bar, Y bar, Z bar, but the camera got R bar, G bar, B bar. It's just the, human observers. You see the top left, top right. We help the right is the manufacturer to select the red, green, blue, the primaries, okay? What is a good prime and what is a good, display? Well, people say it's big, in size. Yeah, it's great. And it's high dynamic range. Oh yeah, very bright, very dark, okay? Very big color gamut. Oh, color is extremely colorful, okay? But another one is very important. How can we reduce the metamerism between the observers? We don't want everybody see different colors. They are all very exciting. But the problem of the current displays, because they are too sharp in terms of their spectral, their location of the red, green, blue, right, is not quite right. Everybody see the big difference, okay? And appearance, consistency is a problem. So we need to select the right RGB in the right bandwidth and the right peak to give the best the combination in terms of least observer metamerism, okay? Everybody see the colors the same. So that is right, is the goal of that. And then we got lighting. Lighting is changeable. Now, it's, bright, and previously it's cloudy, right? And it's raining. So it's daylight changing all the time. How can we do that? We have the systems, right, to tune the light. So we can mimic the light, right? 1982, London, winter afternoon, light, shine, okay? This is how the cosmetic company evaluate their, performance, okay? And finally, right, now we have a system to measure individuals' color matching functions, okay? Everyone, our visions are different. What you see, the colors is different from mine. And this could be very different, especially, right, when we considering the age difference, okay? So now we have the device to measure the color matching function with great accuracy as well, okay? Right, next, please. So the first, right, we're talking about lighting. Next, please. So the spin-off, right, is mainly from the different industry. So we work with the surface color industry. Most of the systems, right, is working for the imaging, okay, online and in the lab. So this on the left, okay, we got the LEDCube, we got the LED view, and we got the LED panel. Today I'm going to introduce, right, LEDSimulator, LEDSSF, and LEDMax. So these are the correspond to what I mentioned a bit earlier. Okay, so the world is changing. The world is changing to the LED, right? Everything what we are doing, right, is LED tunable. Why is that? Because, right, because of energy saving. Yes, energy, big problem now. But this is the old story, right? But now, right, if you look into the shops, right, there's no fluorescent tubes. It's phased out, right? So that you can disagree with me. It doesn't matter. Okay, look. And also, right, it's the tungsten phase out. Okay, but now the new era is LED, right? So LED is simple, energy saving, long life, blah blah blah. Many, great advantages. Okay, but what is facing the service industry? We needed the new lighting to adapt to the new environments. Everybody's using LEDs, right? So 3000K, 4000K, 5000K. But the lighting, we needed to, spot on, okay? So next, please. Oh, sorry, this is right, just a very brief mention, right? It's what our technology is being used, okay? So you can see the right is all the mobile company, 100%. Yeah. And the mobile company is there, and the some surface color industries, 250 systems worldwide, 2,500. Sensor related and the surface colors. Sensor related, right, is occupied 90%. 10% is for the service industry. But I'm very proud, right, is that for the 60 institutions, research organizations, universities, they purchase the systems, okay? Exact number is 63. They produce the 350 papers, okay? So if you want the papers, right, using the Southern Light systems, okay? Why is that? It's tunable. It's spectrum tunable. You can tune any source, right? Is the, agree with that. Next, please. Oh, really? Sorry about that. Now is the new sections. Okay, we're talking about the camera sensors. Okay, camera sensors is the key. Okay, all the mobile companies, right? They adopt the different technology, and what that means, right? The sensor is different. There are different theory behind. Okay, so camera sensors, right? Previously, we do in the colorimetric XYZ way, but now we can do, right, is in the, the spectral sensitivity function. So this is a much more accurate and more convenient way to calibrate your mobile phone to get it more accurate, and you can cover the more conditions. Next, please. So you can see the right is the what is on the top, you have seen it. Okay, we need a light source, we need a human vision systems, and we have the object. Okay, so we have reflectance, we have spectral power distribution, and we come out right is the 2 degree and 10 degree the standard observers. Okay, this is 2 degree, this is 10 degree to define the size of the object. Okay. But for the camera, exactly the same, except, right, the spectral sensitivity functions, okay? Human being, we have colorimetric functions. Camera, what we call the spectral sensitivity functions. They are different, Camera measure RGB, and then the human vision, we come out X, Y, Z values, okay? But in fact, right, they correspond, but not exactly, okay? So if you produce a camera sensors, exactly get RGB agreed with X, Y, Z. This is what we call loose conditions. Okay, so everybody try to achieve that. Okay, so so this is the difference between the human observer and the camera observers. You can consider this. Okay, so you capture images and you look at that comparing with the real thing. Oh, they're not the same. Why is that? It's observer metamerism, because camera disagreed with the human, the human vision. Okay, next, please. So we developed this, right? So now I'm going to criticize, right? What is the existing system now, right? Okay, so you put your chart. So and this is what I say the shade card. Okay, this shade card is familiar with all the imaging engineers, okay? When they sleep, oh, what's wrong with that cyan color? Cyan color is wrong, okay? Because their minds only includes the 24 colors, okay? So they have a test chart, you put it into the viewing cabinet. You take the images from your mobile phone. They look, oh, very close, great, job done. This is what they call characterization, okay? This is how they get color right, okay? But what's the problem, right? Time consuming. I need to put the chart into the viewing cabinet. So the position change a little bit, and the angle change a little bit. It's all different, okay? So you need to get set up right. Take a long time. Secondly, poor accuracy and the precision, okay? So the precision means repeatability. It's not able to get the reliable results, okay? Pretty good, but not perfect, okay? Shade fading and distortion. the card distorted, okay? So this is the 6x4. After 1 year, right, it's bent, okay? It's not flat anymore, right? And then they use only paint materials, okay? They use the 7 pigments to produce all these colors, okay? So it's very limited and unstable of light source. So, I use the very bright, you use the southern light, another one using the X-ray, okay, fine. But they are all different. They assume, right, this 65 is constant, right? So sensor batch the difference, okay? And the sensor parameters, color measurement. So I named, right, all these are the drawbacks, right, for the industry, okay? So what they can do, right? Next, please. So this is the systems, right? The system looks like that. It's like the, a submarine, at the scope, okay? It's coming up and down, yes? So you measure the camera colors, then you measure the spectral of the colors. Altogether, right, is 18 channels altogether. From the visible range, right, is 380 to 700, okay? Yeah, okay. So, and I contact you, okay, right? So the bottom right, look, this is what is being measured, okay? So, and we can, what is the goal, right? It's our work, right? It's this red, green, blue representing the red, green, blue. It's like, eyes response of the camera, or the camera, the responses, okay? So when we do the calibration, now we don't need to go through the matrix. We can just go through the spectral, 31/3. So these are what we call the SSF. You can get it. So every camera in the production line, you got your own SSF, okay? And then it will have an individual performance, okay? It's reflected, individually, okay? Right, so next, please. So this is the one that we measure, that we compare with labs, we compare with the, imaging engineering, and here the Southern Light. So we compare, so we look at the, and the color comparing with the really measured in the viewing cabinet, okay? So the delta R, delta G, delta B percentage error, very low. It's about the 2%, okay? Right, and the one, right, we got, right, it's the left 2, okay? And the left field and it is in the middle, okay? And when we transform to the color difference, okay? So the difference, right, is about 1.3 delta E, okay? So for all these the different instruments, okay? So here, right, is we just show, and they are not just us to produce the equipments. We have the lab sphere. This is, right, is the monochrome meters. We measure the wavelengths by wavelengths, okay? And the IE, right, is using the 31 filters. Show at once, you capture, one images, you compute all these results, okay? So, so this is the typical performance. So what we are saying, right, our system performance is similar or, slightly better than the others, okay? Next, please. So another one, right, this is, right, a new, and the 24 cards being used, right, many years, since 1980 something, okay? Everybody's using that, but they got a problem. I mentioned it before, okay? But now we have a new 24 cards. These are correspond, oh, sorry, these are still in Chinese. So this correspond to our memory colors, okay? So how can I say, right? I have the Caucasian colors, I have South Asian colors, I have African colors, I have the pork and carrot, orange, banana, and green apple, and green grass, and the sky blue, and so all these are the memory colors. What's that for? We are doing the same to do the calibration and to do the image processing. This image is, right, representing 24 colors. We do a lot of the preferred color reproduction work. Thanks very much to the Leeds colleagues as well, helping us to accumulate the data in the COVID period. So you knock people's door. Can you do the experiment for me? I was really moved. Okay, right. Thank you very much. Okay, so now it's being produced 1,000 cars on the market right next month. Okay, so inside there, right, is we are developing software, right, is to you take images automatically you capture these 24 colors and render and then get the color right, get the color beautiful. Okay, right. So next month, right, is just on the still a lot of work to do. Okay, so it's we are not challenging Macbeth's color checker chart. We are not. This is the complementary to or supplementary. This is supplementary to the MCCC Macbeth's color checker chart. So altogether now, right, is our chart, right, will have 30 colors, and together with the original 24 colors, 54 colors, and you can do very good, accurate color, calibrations for your camera. Okay, right. So this is right. It's this is another spectral based. This is the XYZ based, but it's used in the ISP, image signal processing. Okay, in the mobile phone. Next, please. Yeah, now we're doing the vision color matching. So this is very exciting. Okay, right. If we say the modern color science, right? What is modern color science? I will say the individual color vision. So what does that mean? Because our visions are different. So how can we quantify our color matching functions? Okay, what is the benefit? I will mention in the last, but I will say, right, how can we measure each individual's color matching functions? Next, please. So this is the system we developed, okay? When you produce the color matching function, there are two ways to do it. The first one on the left is we call the maximum saturations, okay? You have 3 red, green, blue there. And on the left, you have a half colors with saturated colors. The other half is your job to adjust the RGB to match that colors. This we call the maximum saturation. The other one we call the matching. So what do? You always match the white, but you are using the different primaries to match the white. Okay. So next, please. We are doing the LEDMax is the Max-Williams method. Okay. So we've been at the that's the talk, right? Traced all the way, Stephen. Do you remember? We were sitting there. We were sitting there, right? And we discussed this, okay? And it stimulates, okay? I think, right, is I learned from you and Graham, with 3 of us sitting together. What is the future of color science? What we can do, right? We want the lighting correspond to individual observers. And my job is to make the mobile phone for each individual observers, okay? Our goal is very similar. But how can we do that? We needed to measure each individual's color matching function. So this is system being developed, right? 18, channels LEDs there. So RGB, we divided them into 3 groups there, and we match 11 colors, okay? So you are the observer, you're coming in, you are doing 11 color matches. And after the 11 color matches, we can compute your color matching functions. How? Next, please. So we got your matching results, okay? On the left is the CIE, 2006 2-degree, and the CIE 2006 10-degree observers. So these are what we call standard templates. So we use the standard templates, right? And we modified the equation, the color matching function in 6 areas. The L shift, M shift, long wavelength shift, median wavelength shift, density of the LMS, and the lens density and the macular densities, okay? So what we are saying, right, is everybody, we are different in terms of the color vision. What caused these differences, right? because of this, the parameters, we got the, red-green shift. So the standard is here, but yours, right, slightly move away. And mine is into that direction. But fine, we're still, color normal observers. But we have these deviations, okay? And then, right, it's a density. Our density is different, red, green, blue, okay? And finally, right, it's a lens density and the macular density. That's to do with age, okay? Ronnier Luo, 64 years old, very low, very low transmittance, okay? So my density, right, is very big, right? Because a lot of light cannot go through, okay? So this is, right, it's the typical way to do it, okay? So what do we do? We produce the, LED tunable, systems, allows you to perform the color match. Altogether, right, 10, but, we can produce the even more, okay? But it's enough. Now the question may be, right, is how can we reduce that to get a similar, okay? Because the system is big, bulky, it's all this. And we can apply this, right, in different the areas, okay? So what do we do, right, is then, you look at the lighting. So we have the systems, right, allowed us to tune the spectral, get a good color match on spectrum. And so we can produce any phase of the lightings. It doesn't need to be daylight. It can be indoor, outdoor, some special, lightings, okay? As far as you have spectrum, and we can match that, okay? Human observers, so we can measure it. So how about, we measure from the primary school, middle high, high school, we trace what is the color vision changes over time. How about for the color deficient observers? We can have a very accurate way to quantify the, color deficiency, and observers, okay? So for display, we know the spectral of the RGB and the spectral of the RGB primaries, okay? And the camera, we know what is the sensors, the spectrals. We combine together and with our color matching functions, and this phone will give you what we call the maximum productivity. Okay, you can work well, your productivity is high, and also, right, for your, the visual comfort, because different age give us different contrast. So our reading speed, all this will be affected, and this will automatically adjusted. And finally, right, is to do with the circadians. Okay, we're tired at night. What is the best way to illuminate or display the images for us then to be able to sleep well, have a high quality of sleeping? Okay, so all this, right, coming to play finally, right, is the spectral technology can achieve this. Okay, so so as a scientist, and we produced a lot of the right toys. I call it toys, but we think, right, is a great applications in industries. Okay, all industries are responding. Okay, so next. Oh, I'm sorry. The last one is simulators. Okay, the next one, please. Yeah. Okay. So look at there are two visual fields, left and the right. Okay. On the left, it's a colored textile samples shined by the white light. The white light could be D65, D58 illuminant. Okay. But how about on the right? It's a white. It's just white textures, but you strike the colored light into the white fabric, and we can produce a match. This is we call it the texture metamerism. No, I would just say, right, it's a typical mathematical match. One is you are seeing the light, the other side is you are seeing the color. Okay, and they produce the good color match. Okay, so this is the general ideas they're coming from. Okay, so the designers, right, the most important is to generate your color samples. Okay, so you can collect the marbles, the leaves, all sorts of the materials which some of them cannot be measured by the spectral photometers. Why is that? Too small, okay? Or irregular shape, okay? You cannot measure that, okay? So what you can do, you produce the A match like that, okay? So this is right, XYZ match. Two samples, okay? One is the light on the substrate. Another one is color light, shined by the white illuminant. They have XYZ value, by XYZ value match. So that is the A color match, okay? Right. So next, please. So this is the general, the schematic and the diagram of the systems. This is what you see in front. We are going to do the demonstration later, okay? In front. And in the back, we got two LED panels, 45 degrees apart. So we shine the white fabric using two light panels. Okay, so the back, looks like in the top left. So LED panels, as you can see, is the top right, and then in front is the viewing cabinet. So we use the 11 channels. If you want the UV part match, 13 channels. Okay, right. So what is the performance, right? You can see the P50, 5002, P55, 5524. This is just the examples. So what do we mean, right? The light source go out, right, to the customers. We have the very tight plus minus 10K. So that is very accurate. But the time goes on, so the color will drift. So that is what we call plus minus 50K, 50. Is still considered to be very accurate, okay? And the RA is more than 99. So 100 is the perfect number. So what is the RA, color rendering index? All the colors you see in the outdoor daylight, and we can accurately reproduce in this viewing cabinet. And the metabolism index always grade 8, okay? So 5 pairs of samples, right? You look at the color difference outside and look at the color difference inside. The difference is less than 0.25. Okay, the mean color difference of the 5 pairs. And this is what we call metabolism index. A, B, C, D. And A, of course, is the best. Okay, and that is what we can do, right? So I had to include and the other slides, right? But now, right, is the new improvement. Okay. The customers getting tricky and tricky, right? So the customers, right, is saying, right, now I want to do the high dynamic range. I want to measure the images, right, using the mobile phone from the 50 lux, go all the way to 60, 70,000 lux. I want to simulate the daylight outside. I want to measure the very, very dark, in the dark night, okay? So the system now expand, right? 15 lux all the way, right, to the 70,000 lux levels, okay? And it gives you, right, is color temperature changeable, 3000 K, 3000, 4000, 5000, all this, okay? So next, please. I'm sorry, I'm in the simulator. Why I'm talking about is the lighting now. Sorry, okay? And this color wave, right, is the color selections, okay? So, and what we adopt, right, is the top left. This is, we use the NCS idea, okay? Nature color systems. That is what I preferred, okay? I also like Mansell. Look, Mansell is in the bottom, okay? So when you select the colors by color wheel, the best way to do it, I would say, is the NCS, the color systems, okay? Red, green, yellow, blue, 90 degrees apart. These are the pure red, pure yellow, pure green, and pure blue. And then the color in between, the color combination, the designers permitted that. And in the bottom right is the Mansell's, lightness and the chroma, okay? Once you do the coarse selection and go into the fine selections, okay? So you can manipulate in the very small areas. The people criticize, oh, I'm using the Pantone colors. There's a big gap in between. non-sales, oh, big gap, NCS, okay? But you use the red, it's the digital colorway to do it. There's no gap. So it's always continuous colors to provide, okay? Right. So, so the next, please. So once you select the colors, right, you can it determine whether this color is dyeable or not. So we link with the database, right? We use the cotton, polyester, wool, okay, 3 textile database, together with this coating, okay, coating the painting, okay, and the printing. These are the graphic art printers, okay, and there's another one, plastic, and also plastics, okay, compounding, okay. So we have 6 database. Each one, right, is the more than 1,000 spectral data, okay. So before you send it to the dyers, so we formulate a reflectance, okay. So if it's not achievable, it will say, no, don't use this color. It cannot be reproduced. So they will change another color until it's not reproducible, okay? So this is, right, the link of the whole system together, right? So if you are the designers, okay, Philips, okay? So you select the colors, okay? And you will say you say, hey, this is the color I want, but I don't like that texture, okay? So we have 20 texture to select from, okay? So designers, right, facing the challenge, right, is saying, oh, I select the right colors. I'm not very confident if this colors goes into that textures, okay? But now you can put the colors, right, in the back of the systems because it's just white in the fabric. And then it will really, right, produce the good appearance to the final product. We call the virtual samples, okay? So once you produce that, right, you are saying, oh, I like this color fantastically, right? It's okay. The next, right, is saying, oh, is it dyeable? There's no point, right, to just give the dyes. They cannot dye it up, but the system check for you. It's saying, right, oh, it's dyeable. So we send, okay, right? So so it's all this link together, okay? And what we call color inconstancy index is also provided. It gives you estimation the colors change under the different illuminance. How's the quality of this reflectance, okay? And when you dye up the sample in the dyers, right? The first things that you want to see, hey, how good is it? It's a delta E 0.8, it's good. But you want to see the real samples, but samples in the window. You can light it up, shows exactly the same sample, comparing what your dyings together, side by side, okay? So if they are not happy, all this, you can still have the, modifications there, okay? Everything, right, it's a challenge for the textile industry, right? The color industry, it is, right, iterative, And then designers, oh, not what I want. The dyers, oh, I got delta E0. I got delta E 0.5, okay? This is what you want because your reflectance like that. But no, I want it to be red. But the dyers and the brand owners and the dyers can work together using the same systems with fast speed color communication between different groups, okay? The system is for the supply chain, okay? And today, right, and Su Chen from the Marks & Spencer gave me many new challenges, okay, right? But it's good, it's very much interactive, right? So we understand, right, it's for different types of textiles, the demand is different, okay? For the sport, companies, Adidas, UA, Nike, their requirements are different from the traditional Marks & Spencer type of the applications, okay? So the present and the future, right, is, well, you know what I want to say, okay? So it is saying, right, it's, so now we have tools, we can fine tune the spectrums in any circumstances, okay? We can create a virtual world if we want to do it because we have the spectral data, okay? So using the spectral data, and in and out to do the image processing. I even can create a synthetic environment, okay, and corresponding to a particular individual observer, okay. So so this technology is for you, for everybody, okay, right? So next, I think it's finished. Yeah, okay. So this is my lab, okay. The members in my lab, okay, altogether currently, right, we got about 15, students, okay, right. Thank you very much. Thank you everybody online, okay, right.
Ronnie, anybody got any question to Ronnie? Before we
Come on.
go to online.
Yes, sir.
Hey, Ronnie. Yeah, so I'm really excited about the possibility of personalizing all sorts of things, including displays, based on individual colorimetry. Really something potentially massive in the future. But were you sort of suggesting that with your camera and display you can measure this individual? Don't you need some sort of monochromator to measure people's colorimetry functions? How would we actually measure it in practice?
Okay. So for, Steve, right, I separate them at this moment, right? LEDMax is a system specially devoted to measure colorimetry functions. Okay, so it's nothing to do with the tuning. It's a human tuned the colorimetry RGB. Okay, so that is one way. The cameras, the SSF. Okay, it is just put there. 18 colors you measure, right? So you use the camera, measure 18 times. You also measure the spectral 18 times by the spectral radiometer, and then you compute. There's no human involved. So that is to do with the typical characterization. Do you remember G-Wei? G-Wei used to build the monochrometers, and we measured all this. Now we simplify, okay? Yeah. So it is trying to replace, right? It's the card-based, okay? Card-based, you got a lot of problem. Card-based, right? You're only painting. How about textiles, okay? And only 24 colors, a small color gamut, okay? Look at it, the colors changing, and fading, right? And distorting, but you never take notice on this. So XYZ values being used in 10 years, still based on the same card, okay? So what is the consequence of that? The whole systems, right, is suffered because the earlier model and later model, they have different, calibration profile, and the results are inconsistent. So what we are suggesting, right, is that the previously, right, is a color corrected matrix,